Okay, good morning everybody, let's get started. Today is our 8th lecture and the topic is simple waves as self-similar solutions of the Euler equations. So I'd like to remind you that why do we consider this topic. So the main goal for us is to understand how can we develop and use the finite volume methods. So finite volume method is a method for numerical integration of the Euler equations written in integral form because we want to be able to compute discontinuous solutions, so all types of solutions. And so finite volume method is one of the most, one of the best options for that. And in the finite volume method, the computational domain should be divided into computational cells. Each of the computational cell is called a control volume or finite volume. And the numerical scheme is written as a numerical balance law. So the change of the quantities, mass, momentum, and energy inside one computational cell is defined by fluxes of these values through the boundaries of the computational cell. And the question is how to compute this numerical flux. So in the simplest possible option, this scheme has a 3-point stencil. It means that to compute the n plus 1 here, we need the values here, here, and here at the nth time layer. So once again, within the scope of our course, we consider only explicit schemes, and that is why we need such 3-point stencil. And if you want to understand how to compute this numerical flux, we need to know how to solve the Riemann problem for the Euler equations. Because if we know the solution of this problem, we should use the exact solution or some approximation of this solution in the computation of the numerical flux. And we started the preparation for the solution of this problem. And last time we discussed that a number of features of the solution of this Riemann problem. In the input data of the Riemann problem, there are no parameters with the dimensions of length or time. Therefore, the desired solution is self-similar. That is why, first of all, we should know how to build and what are the self-similar solutions of the Euler equations. The class of self-similar solutions to the Euler equations consists of a constant solution, including those connected through a discontinuity, either contact or shock wave, as well as refraction waves, or more accurately, simple waves. And at previous lecture, we considered shock waves, and I tried to explain to you two aspects. So the first aspect is how to get the necessary relationships that can be used for the construction of the Riemann problem solution. We will do it next time. And the second aspect was just the mechanics of shock waves physics. I tried to explain to you a number of examples when you can meet the shock waves in reality, and some typical applications in explosion safety issues, in aerodynamics and space industry, and so on. Now we would like to consider the second type of self-similar solutions for the Euler equations, namely simple waves or simpler refraction waves. That's the topic of this lecture. So once again, the review of previous lecture, short reminder. So the main result is that we obtained Rankin-Hugoniot jump conditions. Highly likely in literature you will meet this notation. Here d is the velocity of the discontinuity, u is the conservative variables vector behind the discontinuity, and u0 the vector in front of the discontinuity, and f is vector, flux vector. And so you can check that all the relationship, all our Rankin-Hugoniot jump conditions that we derived last time can be written in this form. And we classified them, the discontinuous solutions, they can be either contact waves or shock waves. So contact waves, a contact wave is a discontinuous solution for which mass flow through this discontinuity is 0. It can be if the velocity of gas equals 0 to the left and to the right of discontinuity, or the discontinuity and gas to the left and to the right, say they all have the same velocity. And the shock wave is a discontinuity across which all the parameters jump. There's a gap of all parameters: density, velocity, pressure, temperature, everything. And I provided you some historical background because this result is not so obvious, and people were not sure that the discontinuous solution they really exist. A number of examples. And we discussed what is the Hugoniot curve. So this is the quantitative description of a shock wave. So it's the set of all parameters, set of all states that can reach gas if any shock wave passes through it. We analyzed very important Semplain's theorem, and it will need us today as well. Semplain's theorem that the expansion shocks are forbidden. And the example of its correlation, for example, we consider the so-called Rowe scheme, and which in its classical formulation admits the expansion shocks. And also analyzed gas velocity and explained that the shock wave propagates with a supersonic speed relative to gas in front of it, and with a subsonic speed relative to gas behind of it. So these are the main results from previous lecture, and a number of them will be useful for us next time. Okay, this lecture, I'd like to start this lecture first of all with the linear case. So I'd like to explain, first of all, on the example of a linear hyperbolic system of equations, what we would like to get, and then we will do it for the Euler equations. So suppose we have a linear hyperbolic system of equations in the following form: d over dt plus a d over dx equals 0, where a is a matrix and all the elements of this matrix are constant elements, so they do not depend on our solution. So such system is called a linear system. So we believe that it's hyperbolic system. So it means, so the system is hyperbolic if it's diagonalizable with the real eigenvalues. It means that the following diagonalization procedure is valid. So A equals omega r lambda omega L, where omega r is a matrix of right eigenvalues and omega L is matrix of left eigenvalues, and L is diagonal matrix. And so all eigenvalues here in this matrix lambda, they are real. And there's standard procedure. What can we do if we know this representation of matrix A? We put it here, then we get this equation. Then we multiply it to the left and to the right by matrix omega L, and omega L and omega R. So omega L is inverse to omega R. That is why, so this product gives us identity matrix. And as soon as we have a linear system, then we can put this omega matrix into the parentheses and get this form, and then introduce a new variables called Riemann invariants. R equals omega L u times u, or the same omega r minus 1 u, because this matrix omega r is inverse to omega L. So this vector R is called Riemann invariants, and this is very important variables because it allows us to reduce the system to this one, which is a set of m decoupled advection equations. So the problem is here that the system is coupled. I will show you later a very simple example. So first of all, a couple of slides about theory, and then I try to explain a number of issues on very simple practical example. Actually, this is very simple. This is for the linear system. But what's next? We want to understand the wave's behavior for this linear system. Solution to the Cauchy problem. Consider the Cauchy problem for our system. So now we have some initial data, the vector of psi x, and from this data, we can compute corresponding initial data for the Riemann invariants, because there is the relationship like this one, the relationship between R and U. That is why we can compute the initial data for our Riemann invariants. And for each pth equation of the system, so we have m decoupled linear direction equation, right? And we know the exact solution for each of these equations. So the exact solution is psi p of x minus lambda pt, where psi p is the corresponding component of our exact solution, right? And then we can collect all these solutions to separate linear direction equation into vector. And then this is the solution to original problem. U of xt equals omega r of xt, where each component of this vector corresponds to the solution of one scalar conservation, linear direction equation. That's also actually very simple. So just the generalization of knowledge of the exact solution of linear direction equation. Okay, let's analyze the resultant, the final exact solution. So U is omega r and vector of Riemann invariants. What is it? It's the matrix, it's the vector. So we should multiply a matrix by a vector. And the result should be a vector. So each component of this vector equals to the product of the, for example, the first component is equal to the product of the first line of matrix omega r to the column corresponding to this Riemann invariance, right? So I'm writing that this just the actually scalar product or summation of omega r 1 p. 1 means the first row of this matrix omega r, pth component rp, and so on and so forth, and the mth component of our solution. If you have this form of our solution, we can rewrite it in the following form. It's the summation of R1 to the first column of our matrix omega r, and so on and so forth. But each column of matrix omega r is a right eigenvector. So because omega r is a matrix of right eigenvectors of our initial system. It means that the exact solution of our problem can be written in the following form. So it's a linear combination of right eigenvectors, omega 1, so on, omega m, at each point in space-time, and hence as a superposition of waves propagating different velocities lambda p. So the solution of our problem actually is a superposition of different waves. So each wave corresponds to each eigenvalue lambda p. The scalar values rp give the coefficients of these eigenvectors at each point, and they hence, so in literature you can meet the term strength of each wave. And the requirements of hyperbolicity ensure that these m vectors are linearly independent, so it means that they form bases. It means that the determinant of matrix omega r is not zero, and hence every vector u has a unique representation of this form. The functions rp are also called characteristic variables. So the solution for the linear hyperbolic system of equations look like superposition of these waves with strengths equals to this rp solutions for each linear direction equation. That's the general solution. We're interested in, and I will explain later why, we're interested in a special type of solution, so called simple waves. So that's the topic of this lecture. So what does it mean, a simple wave? So I'd like to show you it on the example of linear system. So we can view the solution as being the superposition of m waves. So actually this is also valid, for example, for elastic waves, and actually this can be of importance for those whose research is not about gas dynamics, but for elastic media, so solid mechanics as well. So we can view the solution as being a superposition of m waves, each of which is advected independently with no change in shape. So the pth wave has shape psi p omega p and propagates with speed lambda p. So this is just the explanation of the previous slide. Actually, these materials are taken from book of Levesque. So I try to combine different sources, because in one sources the material is more theoretical, and so I try to keep some mathematically rigorous explanation of the material, but some other books, they provide more practical interpretation of all the theoretical results. So I think that the combination of both is important. The solution has a practically simple form if psi p is constant in x for all but one value of p. Say psi p of x equals some constant value for p not equal to e. So suppose that all this psi p is the initial data. So suppose that in all the components of our initial data we have constants except just one component. And in such a way, our solution has the following form. Actually, it corresponds to, and the initial data simply propagates with speed lambda I. So for the component which is not constant, right, so the speed is lambda I, and the solution of our problem is the propagation of our, the whole vector psi with this speed lambda I. Since m minus 1 of the characteristic variables are constant, the equation essentially reduces to this one. Nonlinear equations have analog solutions called simple waves, in which variations occur only in one characteristic family. So the special type of the solutions, or special type of laws corresponding to hyperbolic system, both linear and nonlinear, correspond to so-called simple waves, in which only one, in which variation occurs only in one characteristic family. So we would like to build this is the special type of the solution of Euler equations, in which all the Riemann invariants are constant except just one. And it turns out that this solution is self-similar, and it turns out that specifically this solution is necessary for us to construct the Riemann problem solution. So we need to know how to build simple waves, or specifically simple expansion waves. So we the previous lecture, we discussed the Simplin's theorem. So it means that the gas cannot, so the pressure cannot be decreased through the shock wave. But how the pressure decreases in reality? And so it decreases in expansion waves. And we would like today to get this solution corresponding to the structure in which the pressure decreases. So last time we discussed how the pressure can increase, so due to propagation of a shock wave. Today we will discuss how the pressure can, quite contrary, decrease. And it cannot decrease in shock waves. But as I told you, so you understand that that was a little bit difficult, maybe a little bit theoretical. Consider that, so just relax. Right? Consider a very small, very simple example. We consider the following abstract 2 times 2 linear hyperbolic system, and I'd like to show you one more time and explain to you the importance of Riemann invariance. So what does it mean? Why do we discuss all these things? So consider just this abstract system. So it's the example of the of this general case. So here, if you take m equals 2, right? So consider only 2 equations, and consider very simple matrix A. So d over dt plus a dv over dx. So u and v are different, functions. dv over dt plus b d over dx. It means that they are coupled. So you see here d over dt, but dv over dx. So that's not the same as we considered previously, right? And we have some initial condition, and actually it turns out that we have such boundary conditions, so that's not too important now. We want to solve this equation. We want to build some numerical scheme and for the solution of this equation. First of all, let's analyze it. Let's carry out the characteristic analysis. So when you meet this system, first of all, you should know what is it, what's the type of this system, how can we deal with it. So let's write it in the vector form. Then we introduce vector u with the components u and v, and matrix A with the components 0, A, B, 0, right? And again, vector u uv, and you can check that if you multiply this row by this vector, you will get auv, right? And for the second equation, bu here. So indeed, this is the matrix representation of this component-wise notation of our problem. Then the second step, so if we first of all obtain the matrix or vector form of the equation, we should analyze if the system is hyperbolic. For that, we should compute the eigenvalues of our matrix. It can be done computing this determinant, A minus lambda E, where E is identity matrix, and so we just subtract minus lambda, AB minus lambda, lambda squared minus AB equals 0, and two solutions are possible, lambda 1 square root of AB and lambda 2 square root minus square root of AB. And it means that for hyperbolicity we require AB greater than 0. Otherwise, the system is not hyperbolic, and so you're unlucky if you have this problem with AB is not greater than 0, and all this, waves mechanics can be not valid here, and you will get a number of problems. So it's in practice there are known examples of non-hyperbolic models, especially in, for example, two-phase flow models. So if you have two phases and the issue that was discussed for many years, so should we introduce the pressure in both phases or not? And if the phases do not have its own pressure, the system can be non-hyperbolic. And so suppose that AB is greater than 0, it means that the system has two different real eigenvalues, right? Then after that we should compute eigenvectors. I'd like to remind you the general knowledge from linear algebra. How can we do that? We should, so the vector is called right eigenvector if it's satisfied to the following equation: A E1 equals lambda 1 E1. Or if you move it to the left, then it will be A minus lambda 1 I E1 equals 0. Where once again A is our matrix, lambda is the eigenvalue, E is identity matrix, and E1 is the right eigenvector. Then we should find the components of this right eigenvector. So we just write this, what does it mean? A minus lambda E, and then actually the eigenvalues are known, so you can multiply it to any arbitrarily constant which is not 0. It will not change the nature of your eigenvector. So E1 is the first component is square root of A over B, and the second one 1. And in the same manner, we can compute the right eigenvector corresponding to lambda 2. It will change by the sign of the first component. And then we will take the first eigenvector and the second and place it one after another, and it gives us matrix omega R. So you can see it's just the first right eigenvector and the second. So this one, then this one. This is the matrix, diagonal matrix with eigenvalues and the diagonal lambda matrix, and this omega L is the matrix inverse to this one. So you just compute the inverse matrix, and you can check that indeed matrix A is equal to the product of these three matrices. So this procedure is called characteristic analysis, and it can be done for any hyperbolic system that you would like to solve, because so there are a number of theoretical issues and practical. At least if you are not even interested in theoretical issues, the knowledge of these vectors and these matrices gives you opportunity to use known numerical methods. For example, last time we discussed the Roy numerical scheme, the Courant-Jackson-Lewis numerical scheme. So all these methods, they rely on, so they use these characteristic matrices. That is why it would be great if you know these matrices, and then at least you can use the known numerical methods for your system. But okay, so suppose we require that AB is greater than 0, the matrix is hyperbolic. How can we solve numerically this system? First of all, suppose that we did not attain such such classes, such courses, and we propose a naive numerical method which actually doesn't work. So let us construct the simplest scheme approximating both equations using Courant-Jackson-Riesz numerical scheme. So okay, A is, suppose we can choose A is greater than 0 and B is greater than 0. Then AB is greater than 0, and the system is hyperbolic, and we can remember that, okay, if this coefficient is greater than 0, the stencil, left angle stencil should work, and maybe it would be great if we construct the scheme in the following manner. So we will use the explicit Euler scheme for for the approximation of time derivatives, and upwind. So we know the concept of upwinding. Okay, we will take the upwind approximation for derivatives with respect to x. But the problem here that here we have u and here v, and here v and here u. But suppose that maybe that's okay. And you can check that obviously standard consistency check shows that the scheme has the first order accuracy, because actually we use reasonable approximations for derivatives, right? We can expect that the result will be great, but actually the scheme is unstable. So you can choose some initial data and try to implement this numerical scheme, and you will see that it doesn't work. And the problem is that this scheme is unstable. We didn't discuss the so-called von Neumann stability analysis. It's a very important theoretical approach. I think I will discuss it in more detail later on the lecture about the general concepts on the stability, consistency, and convergence for partial differential equations, including nonlinear case. I think one of the following lecture will be about that. But the essence of this method is the following. We choose this, so we say, okay, let's choose the solution UMN, VMN in the following form. C1 or C2, lambda n, E, this is the complex 1, M alpha. According to Lach's definition of stability, so our solution should be bounded, right? The scheme is stable if the amplification factor lambda satisfies model lambda is less than 0. It means that our solution should be bounded in time. So it means that the scheme is unstable. However, if we put I just explain you the result. And so the von Neumann stability analysis, the essence of this analysis is that we choose the solution in this form, then put it in our numerical scheme, and try to find the relationship between parameters of our scheme. The most important is we try to find the time step t, the function of alpha, a, b, and h, in such a manner that our solution should not grow in time, the amplitude of this solution. And it turns out that it's not possible to do here. So it means that this scheme is unstable with respect to initial data. And that is why the scheme is not be used. But what should we do in this case? Instead, we should use the Riemann invariants. So we should build our scheme based on Riemann invariants. So how can we write our system in this case? So dr over dt plus lambda dr over dx, where r is omega l u, and omega l is inverse to omega r. And so uv, again, we should multiply this matrix by a vector. And so these are Riemann invariants. We can call them R1 and R2. And now we can, made a transition of our initial coupled system to a set of independent linear direction equation. And now we can apply the Courant-Jackson-Riesz, for example, numerical scheme to each of these two equations, but not to initial equations, but to these equations for the invariants, using appropriate upwind stencil. So here we use, okay, yes, Courant-Jackson-Riesz numerical scheme, but here R1, R2, and here R1, R2. And here is lambda is greater than 0, that is why we use upwind stencil here, m minus m minus 1, and here the lambda is negative, and we use the corresponding upwind stencil for the second invariant, m plus 1 minus m. Because depending on the sign of lambda, we should use either this stencil or this stencil. We discussed it. And it turns out that this scheme works well. So actually, this is the how the current external numerical scheme should be used for the solution of linear system of equations. Riemann invariants are important not only for the numerical solution itself, but also for the correct statement of our problem. So the correct statement of boundary conditions demands one condition for R1 at the left boundary and the condition for R2 at right one. Why is it so? Because we can consider for example, we would like to solve our equation on the interval from 0 to 1, right? And we can plot the characteristics of the first family and the second family. And for these characteristics, dx over dt equals square root of AB. They have, positive angle, this one, a positive slope. And it means that for the left boundary, we have characteristics which comes from outside of our computational domain. And we do not know the information on the left boundary. It means we should specify the boundary condition for this Riemann invariant R1, because this invariant comes from left to our boundary. And we do not need to specify any conditions for this R1 at the right boundary, because all the information comes to the right boundary along this characteristic dx over dt equals to square root of AB. And quite contrary, if we consider invariant R2, so the slope of these characteristics is like for blue curves, and they comes and they bring some information from outside the domain through the right boundary. It means that we should specify the boundary condition for R2 for the right boundary, and we do not need to specify any conditions for R2 on left boundary, because the information along this characteristic comes from inside of our computational domain to the left boundary. That is why, this very simple example demonstrates a lot of concepts. So why do we need Riemann invariants? That generally speaking, we can build, bad, round, naive numerical methods if you don't take into account the structure of our numerical of our problem. And also very important, the correct statement of the problem. For the correct statement, we should also understand the behavior of characteristics. So in fact, the number of boundary conditions is defined by a number of characteristics that comes from outside of our computational domain, or of our domain. And for the I will show you that for the nonlinear case, it depends on speed of sound and so on. So okay. Once again, what is the logic of this lecture? We would like to, to know self-similar solutions of our Euler equations, and these solutions will be simple waves. And I explained to you that what does it mean a simple wave on the example of linear hyperbolic system, and also provided you a simple enough example of the importance of this representation of our system using Riemann invariants. Okay. Now we can move on with Euler equations. We have already discussed many different forms of Euler equations. So we started with this conservation form, or more exactly, component-wise notation. So this is the most suitable for numerical solution, and if you open the papers, you will see apparently this form for the Euler equations: mass conservation law, momentum conservation law, energy conservation law, entropy inequality, and we should specify somehow the equation of state, epsilon, because the total energy is the kinetic term and the total energy term. And so once again, we work with the ideal gas equation of state only. And this is the conservation form component-wise notation, and this is conservation form vector notation, which is much more compact. So we introduce vector of conservative variables, flux vector, and then all these can be written in very compact form like this one: d over dt plus d of u over dx equals 0, where flux depends on our unknown solution. So you should know this. So for many times we use it. What we would like to do now, we can analyze these equations, but that's a bit difficult. So this notation is very convenient for numerical solution. So in programs, usually you should have a vector of conservative variables, because the finite volume method is written in terms of conservative variables. But for theoretical analysis, that's not so easy. I have shown to you these, how to compute the Jacobian matrix A for this system, and for that we should compute the partial derivatives of this component over these components, and that's a bit so difficult. For theoretical analysis, the vector of primitive variables is more convenient. Actually, there are a number of numerical schemes that are also based on primitive variables, and also a number of reconstruction procedures. So we will discuss later. A couple of lectures will be about the construction of high-order numerical methods, high-order monotonicity preserving numerical schemes for hyperbolic equations, and a number of methods. They use this primitive variables vector for reconstruction of the solution. So anyway, the system of the representation of all the equations using primitive variables is also important. So let us now transition to the primitive variables form of the Euler equations, starting from this equation. How can we do that? That's also actually useful manipulations that can be used in different procedures. So consider a mass conservation law, d over dt plus d over dx rho v. So here v is the velocity. So the general approach is expand the parentheses and to compute these derivatives as the derivative of complex function, which is equal to product of two functions. So d rho over dt plus, and we expand the parentheses, rho dv over dx plus v d rho over dx equals 0. So we want to get the time derivative for rho, v, and p, right? So rho, u, and p, and have only derivatives of these variables with respect to x. It will mean that we obtain the form of notation of our Euler equations in primitive variables. So for mass conservation law, everything is very simple. So this is the first equation. Now we can consider momentum conservation law, and the idea is the following: we again expand the parentheses, and we use the mass conservation law to simplify the obtained equation. So rho dv over dt plus v d rho over dt, we expand this guy, and then we expand this guy. And we can see that if here we put v away, we will get d rho over dt plus d rho v over dx. It equals 0 because it's mass conservation law. And the momentum equation looks like this one. This is the equation of motion for a fluid first formulated by Euler in 1755. So nowadays, usually the whole system of equations for inviscid gas is called an Euler equation system. But historically, this equation was called the Euler equation. So he derived this momentum equation. And so this historical equation can be obtained on this way. And the energy equation. So energy equation is a bit more difficult, but actually, again, that's not too difficult. The idea is just the same. We expand this parenthesis and try to find the equations that we have already analyzed. Here we can see mass conservation law, and so the notation is slightly different. So here I wrote to you, it was E and epsilon previously, now it's E and E. So I need to to check this presentation and have the unique notation for all the variables. I'll do it later. And so then we use this expression for total energy and compute the derivative with respect to t here. And for example, d over dt of v squared over 2 equals to 2v dv over dt. That is why we have it here and here. And so everywhere we take into account that total energy is the kinetic term plus internal energy, and put it here. And then we again can find the terms corresponding to the equations that we have already analyzed. Specifically, we can find that these three guys are momentum conservation law or this Euler equation here. And then we have this, our energy equation reduces to this one, and then we should have the last step. The last step is the use some form of equation of state. So for the ideal gas equation of state, again, we can put it here and just carefully compute the derivatives with respect to p and rho. So the differentiated is a complex function equals to the ratio of one function and another function. And after not very difficult manipulation, and again after applying the mass conservation law, we will get this very, very simple actually equation for pressure. So because the components of our primitive variables are density, velocity, and pressure. That is why we should get the equations for density, for velocity, and pressure. So energy equation is equation actually for pressure. And again, this gamma is only because we use the ideal gas equation of state. Let's summarize. What did we get? The Euler equations in primitive variables, component-wise form: mass conservation law, momentum conservation law, and energy conservation law. Once again, these equations are just the same as the Euler equations we have already analyzed, but written in primitive variables. And we would like to use the vector form, matrix form. Then we introduce matrix A. And so dw over dt plus a dw over dx equals 0, where A, but here A is a nonlinear matrix. So here A depends on unknown functions, v, rho, and p. So once again, this system is more convenient for numerical analysis because it's much more simple than conservation form of Euler equations, and also a number of numerical techniques also rely on this notation. Now we have two goals. The first goal is to analyze this Euler equations, this system of Euler equations, and try to do characteristic analysis. So we want to find eigenvalues, eigenvectors, and understand the wave structure of these equations. So this is the first goal. And the second goal, based on this analysis, on these wave structures, try to build self-similar solutions corresponding to simple waves. So we still want to understand how the self-similar solutions should look like. So three goals. We will start with the first one. First of all, let's find the eigenvalues of Euler equations. I have already explained to you that eigenvalues should be v minus c, and v plus c. But here it's just obvious. So for this matrix, we compute this determinant, and it can be computed very easy. And it's obvious that eigenvalues are v minus c, and v plus c, where c is square root of gamma p over rho. And once again, this speed of sound appears naturally from the analysis of Euler equations. It's not postulated. So in the last lecture, we obtained the speed of sound as the limiting speed for the propagation for the shock wave with very, very low amplitude. So this is the physical interpretation, but also it was obtained from rigorous mathematical analysis. On the other hand, it's very important part of this eigenvalues. What can we say? So we used ideal gas equation of state. That is why gamma. Actually, we should demand, like for this, for that very simple example of that we considered. So in this example, we said that for the hyperbolicity AB should be greater than 0. In the same manner, the system is hyperbolic if this guy is greater than 0. For the ideal gas, for sure, gamma p over rho is greater than 0. But if you will consider some media with a much more complex equation of state, it's possible that something that will be here will not be greater than 0. And there can be issues regarding this one. So Generally speaking, if you keep some general equation of state, you will get another equation for energy, and you will get here dP over d rho for constant enthalpy. And for the system to be hyperbolic, you should require that this guy, under the square root should be greater than 0. This is very important result. So I'd like to remind you these pictures from, again, previous lecture. I tried to explain to you the general structure of the Riemann problem solution. So, and I told to you that that the solution of the Riemann problem for the Euler equation consists of 3 waves. So one wave is a contact wave, and 2 waves, right and left, and each right and left wave, it can be either a shock wave or expansion wave. It corresponds to this structure. So this eigenvalue lambda 1 equals to V correspond to contact wave. And these 2 correspond to waves propagating to the left and to the right relative to this contact discontinuity. That is why this, there is a strong relationship between the structure of the solution of Riemann problem and the structure of these eigenvalues for Euler equations. And once again, so previous lecture we discussed contact wave and shock wave. Today I would like to explain to you what does it mean refraction wave and how to compute parameters inside this refraction wave. And next time we will combine everything together. Okay, so we found the eigenvalues of the Euler equations, the V minus C, V plus C, and if gamma P over rho is greater than 0, and that's true for gas dynamics, it means that eigenvalues are real, and that's great. Now we need to check that eigenvectors, they form a basis, they are linearly independent. I have already reminded to you how to compute eigenvectors, right? That's why I showed you this very simple example. In the same manner, we can compute the right eigenvectors omega 1, omega 2, and omega 3 corresponding to these 3 eigenvalues. It has already been done for many years, many years ago in different books. You can find this result. The first eigenvector will be 1, 0, 0. This is the second one, and the third one, where C the speed of sound. Then we can compute the matrix of left eigenvalues. You can just take inverse to this matrix. It will be like this one. So all the determinants are non-zero, and this is the matrix with eigenvalues. And this is the diagonalization of our matrix A. So it's the proof that Euler equations it's a really hyperbolic system of equations, right? Because we have real eigenvalues, and the determinant of all these matrices are not 0. That is why we can expect the full system of waves for these equations, and that is why we would like to understand this full system of the waves. Okay, so we know this diagonalization. If so, we can try to do the same procedure as previously, as here. I mean this one. So we knew the diagonalization, and then we put this matrix here, and then step by step we obtain Riemann invariants and so on. Let's do the same thing for the other equations. But the problem here again that the system is nonlinear. So we consider our Euler equations in primitive variables. We computed this matrix. We know this representation. We know all these matrices. We put it here and multiply the left and so both sides by omega r to minus 1 or omega l. And we will get this form. And that's it. The problem is that here we are not able to put omega l into parentheses, because now omega l is a function of w. So now it's nonlinear, so it's the nonlinear system, and this is the function of w. Instead, here we should stop and write the component-wise form. So once again, what is omega l? It's a matrix, 3 to 3 matrix. And W is a column with a vector with 3 components. So this is a product of matrix and a vector. And let's compute, and as a result, there will be a vector. And here, so the result will be a vector. Let's compute three components of this vector, the resultant vector. For that, we should compute that, okay. So it's the component corresponding to product of the first row of our matrix to the column. So these are the pk components of our matrix omega L, and these are omega k. So for k equals 1, it's density. For k equals 2, it's velocity. For k equals 3, it's pressure. Okay, and omega L, pk are the components. What 1, 0, and this guy. For k equals 2, 0, 1, and this guy, and so on. So actually, this is, I'd like just to explain to you that it looks it looks a little bit horrible, but actually it's very simple. So all these objects have already been shown and discussed. So this is the first component of this vector, lambda p, because lambda is diagonal matrix with all this lambda on the diagonal, and this component. We have three rows, so p equals to 1, 2, or 3. These three conditions are called in literature compatibility conditions along the characteristics. And that's again, I'd like to. I'd like to stress out that this is just all these are different form of notation for the same system. So you should understand that these, three equations actually written in this one row. This is just the same as for example, this one. So, but this is, physically understandable, intuitive form of notation for Euler equations. And this is more theoretical, but also important form in form of the same Euler equations written in the form of compatibility conditions along the characteristics. And before the finite Euler methods were widely used, people tried to use, and they created numerical methods based on approximation of these compatibility conditions. So from historical point of view especially, but also nowadays for a number of numerical methods, these compatibility conditions are also important for the construction of numerical methods as well, not only for the analysis of properties of Euler equations. Okay, let's have a break here and continue with the analysis of these compatibility conditions along the characteristics. So, okay, we obtained these compatibility conditions along the characteristics as a result of characteristic analysis of the Euler equations. What's next? Next, let's specify what did we obtain for each component. So, what is W? I just remind you that this is vector of primitive variables, rho Vp. What is omega L? Is the vector of left eigenvectors. And lambda p, lambda 1 is V, lambda 2 is V plus C, lambda 3 is V minus C, and we just specify what does it mean. What is the component-wise notation for compatibility conditions along characteristics. Actually, in a number of books, you can find the following, words and manipulations. Sometimes people do not use these matrices and so on, and especially in books more about practical issues, for example, about theory of explosions and so on, where still people need some information about gas dynamics. Authors say, let's manipulate with our initial conditions, let's multiply them by something, let's add, subtract, and so on, and after these manipulations obtain this form notation, and that's it. But I don't like this approach. I think it's important to show the formal way how to obtain these equations. Here, at this moment, for the linear case, we were able to introduce Riemann invariants. V equals omega L W, where omega L is a constant matrix for the linear case. For the non-linear case, we are not able to do that. Instead, we can introduce dV equals omega L dW, where dV is differential. And omega L is a function of our primitive variables vector W. And the components of this vector V will be V0, V plus, and V minus, called Riemann invariants here in this case. This 0 plus and minus corresponds to 0 plus and minus eigenvalues of our system. That is why, again, sometimes in literature you can meet 1, 2, 3, but so it's useful to keep these indices to illustrate the correspondence between these Riemann invariants and eigenvalues, and in terms they are associated with different types of waves. Why is this notation correspond to Riemann invariants in the nonlinear case? Let's understand that. So okay, so this is component-wise of compatibility conditions along characteristics. Then we can, here a little bit manipulate with this, so just arithmetics. We just collect everything. We want to have v plus c, and v minus c. So these equations look like the advection equation. Why is dv equals omega L dw correspond to Riemann invariance here? Let's compute. Let's use omega L here. dw is d rho dv dp. And in this case, this condition defines the following dv0, dv plus, and dv minus, like this one. And we can see that indeed, take into account these conditions which comes from compatibility analysis, that they can be written in the following form. So it means that if we introduce v sub 0, v sub plus, and v sub minus in such a way, then compatibility conditions along characteristics will look like this one. So, and these conditions, they are similar to system in the Riemann invariance for the linear case. But again, that's not the case here, because here v, c, they are known, and so still all these equations are not independent. So they are not independent. Say they're all coupled. But anyway, they have a form which is similar to those. So I provided to you at the beginning of the lecture. And once again, these are the same Euler equations. The same Euler equations, but now they are written in the form of Riemann invariants. The following analysis. Okay, so we introduced the Riemann invariants, but not in the same manner as it was for linear case. Okay, so it was linear case, this is non-linear case, and if you introduce V in such a manner, our system can be written in the form which looks like the system with Riemann invariance for the linear case. And what does it mean for the linear case? When we have the full set of characteristics, we can say that the solution of this problem is that Riemann invariant is constant along characteristic, right? And for the linear case, we can integrate our system of equations separately for each Riemann along each characteristic. We can say the same thing here. So, okay, we have three invariants, dv0, dv plus, and dv minus, and they should be constant along characteristic dx over dt equals v, dx over dt equals v plus c, and dx over dt equals v minus c. So, just like in the linear case, we can formulate our equations as these three conditions. So each of the Riemann invariant should equal 0 along characteristic, and so this characteristic is called C0 characteristic for the Euler equations. This is C plus characteristics, and this is C minus characteristic. And the problem is that these equations cannot be integrated analytically, because this is non-linear system. Only these conditions can be integrated analytically. What does it mean? We can remind the formula for entropy. This is entropy of ideal gas, and then we can compute the differential of this S. And if we do that, we can see that this differential of entropy is proportional to d rho minus dp over c squared. D rho minus dp over c squared. And if dv0 equals 0, it means that ds equals 0. So it means that entropy is constant along characteristics dx over dt equals v. So this first condition can be integrated analytically. And so it means that entropy is constant along the characteristic dx over dt equals 0. And actually it means that entropy of each gas particle remains constant in time throughout the smoothness of the flow. So it means that actually if you don't consider shocks, so our third equation of our system, energy equation, can be substituted by the equation ds over dt equals 0. So energy equation can be substituted using entropy equation. So entropy is constant along this characteristic. But here we are not able to, and this is the condition for plus Riemann invariant. This is for minus. There are some misprints. There should be v minus and should be v minus. I will correct it later. So characteristic form of Euler equation in the form of Riemann invariants along which propagate along the characteristics. So actually this topic is very complex, and this picture illustrates that. So it's very difficult to intuitively understand the mechanism of propagation of waves in compressible media, because as follows from equations, in compressible media, consider some point, and this is the domain of influence. So we have waves of three types. So this green line is entropy wave. It corresponds to motion of media itself. So we have a media, it moves. And inside media we have waves that also moves. And they can move in different directions. So this dx over dt equals v is called entropy wave. And we just proved that entropy is constant for this wave. Dx over dt equals v plus c and v minus c, they are called acoustic waves. And the problem is here that the velocity of propagation of these waves depends on c, speed of sound, v plus c and v minus c. And that is why, again, the concept of speed of sound is very important, because the flow can be supersonic and subsonic. What does it mean what does it mean for this picture? So suppose we have a supersonic flow. It means that v is everywhere greater than, for example, c. It means that inclination slope of all these characteristics, so the same, not the same, but they propagate in one direction. So v minus c, v, and v plus c, they're all greater than 0. And suppose that, for example, we have subsonic flow. It means that this guy, v minus c, is less than 0. And it means that, so it will propagate this in this direction. And it means that in compressible flow, in case of subsonic flow, each point can affect the state of your media both downstream and upstream. So a number of characteristics will influence the downstream state, and the number of characteristics will propagate upstream. And suppose you solve the problem, you have boundaries, and you need to specify boundary conditions. And in compressible flow, in compressible media, the problem is that these characteristics, they sooner or later reach, in the subsonic case, boundaries and will interact with boundaries and so on. So it's a very complex problem. That is why there are some of art how to impose boundary conditions. For example, if you have a subsonic flow, so what's the problem? So, for example, you compute some duct or some part of your engine, and in reality, you do not have some open boundaries and so on. You have walls or something like that, but you're not able to compute the whole device. In your simulation, you should use some planes in which you provide some inflow boundary conditions. But which conditions should you take? The problem is that for the subsonic case, the flow in your domain will affect your inflow boundary conditions. And so that's a problem. That is why people introduce a number of numerical representation for the same, from physical point of view, boundary condition, because of this very complex mechanics of wave propagation in compressible media. And this is only even one-phase flow. You can imagine multi-phase flow when each media is compressible, or some compressible and incompressible. So it's very difficult. If we indeed try to understand how all this waves propagates. Sometimes, for sure, if you're an engineer, so for sure, in some cases, good numerical methods can solve all these issues instead of you. So if you have some good numerical method, you can expect that everything is already inside and it will get the correct solution. But actually, usually not, because it's your responsibility how to, at least to impose correct boundary, not correct, but so realize the influence of your boundary conditions on your result. For example, if you compute subsonic flows. That's it. So in all the equations, we have three types of waves, and this is the domain of influence, how this point, the region for which this point influence, and this is the main dependence. It means that the state of gas of this point is determined by different ways. So in contrast to linear case, here all characteristic lines, they're curvilinear, they interact with each other and influence each other. That's the point. Okay, so we finished with the first goal. We would like to. So our goal was to analyze, to carry out characteristic analysis of Euler equations, and we carried out the characteristic analysis, and I tried to explain to you the possible waves and the possible so a number of another forms of Euler equations. That this is also the same Euler equations. They're written in very unusual, maybe strange form for you, but actually they are all the same. And actually you can build numerical methods based on these equations. But for us, the importance is more theoretical. But now we want to use all these mathematics to build self-similar solutions of all the equations in the form of simple waves. So once again, I'd like to remind you. So we discussed it last time on previous lecture. What does it mean that the solution is self-similar? It means that the solution depends on x and t as x over t. So it depends on x and t not independently, but it depends on psi variable equals to x over t. And from a practical point of view, it means that your solution, the Riemann problem stretches in x direction, but the structure remains the same. So this is a shock wave, this is contact wave, and this is the expansion wave, and actually this is a simple wave, and we want to know how to describe the solution here. And actually that's our current goal. If we want to build self-similar solution, then we won't use these compatibility conditions. And here we have dwk over dt, and here wk over dx. But if we say that our solution is self-similar, we can specify that dw over dx is not just dw over dx, it's dw over d psi over dx, right? And this guy is 1 over t, because x and t are independent variables, and d psi over dx is just 1 over t, right? And so this is how the derivative with respect to x of our vector should look like. And w over dt, just the same. And now we should compute this d psi over dt, and this is function 1 over t, and the derivative is minus 1 over t squared. And x is constant here because x and t are independent variables. And we obtained the specification of these variables in case of self-similar solution. And then we should put them into compatibility conditions. We put them into compatibility conditions and just collect the terms. So we have dwk over d psi here and here. It comes from derivative with respect to time. This comes from the derivative with respect to x. But now we could combine them because we have the same dwk over d psi, right? And here, yeah, we should multiply by t, and here we have x over t, it's psi, right? And here we have lambda p minus psi. So the compatibility conditions for the case of similar conditions are, more compact, and they are simpler. And now we can solve this system of equations. So we want to find self-similar solutions. They are defined by this condition. Once again, what does it mean? W is rho Vp, and omega L is the matrix of left eigenvalues. We can specify this general form in component-wise form. So all the solutions, self-similar solutions, should satisfy to this system. we can see the following structure. So it's the product of two parentheses, 1, 2, 1, 2, 1, 2. And here is lambda minus psi, lambda minus psi, lambda minus psi. What are possible options? The possible options are the following. Psi equals lambda 1, then it is valid because it's 0. And then for these equations to be fulfilled, this guy in parentheses should equals to 0, and this one. This is the first solution. The second solution, psi equals lambda 2, and then this equation is valid. And here it means that this is not 0 and this is not 0, then 2 parentheses equals 0. Or the third option, c equals lambda 3, then it equals 0, and these 2 parentheses equals 0, right? So 3 possible solutions, because psi could be either lambda 1 or lambda 2 or lambda 3. So we have 3 different solutions. So we need 2 non-trivial. For example, consider the first. Consider the case psi equals lambda 2. So suppose psi equals lambda 2, then it's 0, and this condition is valid. To solve the full system, we should say that it should equal 0 and it should equal 0. So we say that if psi equals lambda 2, then the second. So we have these two conditions. At this moment, it looks like just arbitrarily, very horrible, terrible, equations with no physical sense. But I'd like to provide some physical sense for that. How can we do that? Consider this equation, and let's remind the formula for isentropic process. So the process in which entropy is constant is defined by P over rho to gamma equals constant. We reminded on previous lecture when we plotted Poisson adiabatic curve. Let's compute the derivative of these left and right parts with respect to psi. Then it will be 1 over rho to gamma dp over d psi. So it's a derivative as a derivative of a complex function. So p depends on psi and rho depends on psi. So this is derivative for p, and this is derivative for rho. And after manipulations, we can see that this equation is just the same as this one. So we did not. So there was not some requirement or something like that. But on the way of construction of self-similar solution of Euler equations, we obtained that for the self-similar solution of Euler equations, one of the conditions is the s over the psi equals 0. That's the mechanical sense. So the self-similar solutions are such type of flows in which the entropy is constant. And this is the third equation. And it's also possible to show. Okay. Before the manipulations, I'd like to show you the connection of these results with the results from previous lecture. So it was a slide from previous lecture about the simplest theorem. I'd like to remind you that we plotted the Hugonio adiabatic curve. It's the red one, right? And it goes to negative pressures, and we discussed that that's wrong. And we said that only processes with delta S greater or equal than 0 are possible. And then we plotted this blue curve corresponding to Poisson's adiabatic curve, adiabat, and only states higher than this blue curve are possible. That is why this red curve is forbidden. And I told you, so this, for example, consider this state. So the pressure in this state can be increased in the shock wave. But how the pressure can be decreased in this state? And the answer is that this blue curve is not only to show that this red one is wrong. Actually, the pressure in this curve, the pressure in this point, indeed can be reduced along this blue curve, and this blue curve corresponds to solution that we obtained, expansion in a simple wave. So we obtained that the self-similar solution of Riemann problem correspond to the solution in which ds over the psi equals 0. But this is the state where ds equals to 0. And it means that this red curve, together with this blue line, they form all possible states that can reach gas when a shock wave, either a shock wave or a reflection wave passes through it. And they are combined, they are coupled in a smooth manner because, as I told you, and you can check that, they have a second order contact at this point. So once again, so this blue line is not only to show that this red part is wrong. Indeed, the pressure in gas should decrease. So the points on this blue line correspond to the states of gas with decreased pressure. So expansion in a simple way. And so it's maybe not so interesting, but actually we can work with this expression and obtain the formula for Riemann invariant for ideal gas. So in many books you will find this formula. How can we obtain it? So this is the third equation, right? From the second equation we have P over psi. It corresponds to isentropic process. And then we should work with the expression for speed of sound. C squared equals gamma P over rho. Then we should take derivative from the left and from the right side. And after manipulation, we obtain the relationship between the derivative from speed of sound and density. And put it here. And finally, we obtained this expression, V plus 2 over gamma minus 1C over psi equals to, and it's possible to show that this is exactly expression for V plus. So I'd like to remind you that we introduced these Riemann invariants here, V plus. So we obtained that all the equations can be written in three equations in the form of propagation of Riemann invariant along characteristics. So this is V plus Riemann invariant. And it's possible to show that the third equation corresponds to V plus over psi equals 0. Let's combine all the results together. So we obtained that the possible self-similar solution of all the equations called simple wave or Riemann wave. So in Russian literature, they also called Riemann wave. In English literature is also called. It's usually called simple wave. Is the solution defined by the following three conditions? This is the characteristic line dx over dt equals v minus c, because this one we say let's take psi equals to lambda 2. So we analyze this case. Psi equals lambda 2, then also these two parentheses equals 0. Then entropy is constant. We proved that the second condition corresponds to this condition. And the third one, so this Riemann invariant is constant. And if you consider this picture for Riemann problem solution, these formulas define the solution here inside this reflection wave. It's possible to say, considering the another case when xi equals lambda 3, that the solution here for the right reflection wave corresponds also to simple wave, correspond to when the right Riemann invariant equals 0. These expressions will be used next time to derive the conditions, to derive the formulas inside this reflection wave. I think when we will construct it, it will be more understandable for you. For sure, I understand that it will be difficult, especially these manipulations. But nevertheless, so the main idea that may be here, that we just formally shown how to build self-similar solutions of all the equations and obtained all this formula from this consideration. As like for the lecture with shock waves, actually I tried to obtain formulas that can be used for the construction of Riemann problem solution, and also I tried to show you the real examples of the shock waves. Here also, so we obtained the necessary mathematics that can be used to construct Riemann problem solution, but also it's possible to show a number of problems or flows in which the simple waves exist. For example, so last time I explained to you that actually shock waves, the Rankine-Hugonian jump conditions usually are written either for steady flow or for unsteady flow. And the typical example from aerodynamics is when we have a stationary shock wave, detached shock wave, when we have a steady flow around somebody. And in case of moving shock wave, the example is, for example, explosion is in a duct or in a mine. So suppose we have, this just a channel and sudden release of energy, for example, explosion. And then the shock wave will propagate. And now we can imagine that we have not the inert media, such as air, for example, or instead we have some reactive media, for example, methane air mixture or hydrogen air mixture or something like that. So any media that can burn. And I'd like to show you the example where this simple wave solution that we obtained exists, explicitly. So one of my field of expertise, one of my field of interest is the flows with detonation waves. So detonation wave is a supersonic combustion wave. So if you have a shock wave, so this is the picture once again. So this red curve is Hugonian-adiabatic curve corresponding to a shock wave. So if you have a shock wave in just an air, in time the velocity of the shock wave will decrease if you organize it somehow due to different losses, friction with walls, and so viscosity and so on. So in one Euler equation, the shock wave will propagate with the same velocity, but in reality, right, the shock wave, the speed of shock wave will decrease. But if the shock wave propagates in reactive media, behind the shock wave we have the pressure rise and temperature rise, and this temperature rise can initiate chemical reactions. And in chemical reactions you have the energy release. And it's possible to have the regime when the decrease in velocity of the shock wave is compensated by the energy released as a result of combustion. And so the detonation wave is a complex when the shock wave propagates with, on average, constant velocity due to combustion behind the front of the shock wave. And actually, detonation is just it's an explosion. It's a very dangerous regime in coal mines, for example, because the mixture can burn, in subsonic mode. It will propagate somehow with the flame and so on. But detonation is just an explosion when your mixture, your media burns in a wave which propagates with a velocity of several kilometers per second. And this regime is harmful for people and very dangerous for people. On the same time, this detonation is considered to be a very promising mechanism how to build the promising engines, rocket engines, because it was shown for many years ago that theoretically it's possible to organize regime in an engine using the combustion, detonation and combustion, which will be much more effective in comparison than existing constant pressure, constant volume cycles in these engines. So anyway, closer to our topic. So when do we have this simple wave? So if you have the problem about the distribution of parameters behind the propagating detonation wave, so this is a detonation wave, it turns out that this part of the solution will be a simple expansion wave, simple wave. The wave that is explained by a relationship we have already discussed. So one more time, what does it mean a detonation wave? It's a sort of advanced topics, but it relates to we have discussed. Actually, we have everything in hand to understand that. So suppose this curve, so the curves in P at a space. So the red curve is Hugonic adiabat, or we call it Hugonic curve, but actually usually Hugonic curve correspond to curve with heat release. So the red curve was for inert media, for example, for air. It can be shown that if we take into account instantaneous heat release behind the shock wave, then we will get this green curve. So green curve corresponds to Hugonian curve with heat release. it corresponds to all possible states of gas behind the shock wave with instantaneous heat release. And it's possible to prove that if we plot this tangent line from the initial state to this green line, it will be a point called Chapman-Jouguet point. It's the point corresponding to the parameters behind this supersonic wave propagating in media. So it's known that for a given media, for example, for given gas, this velocity of detonation wave propagation will be just the same. So it's the characteristic of the medium. And it corresponds to this point called Chapman-Jouguet point, after names of French researchers who studied this phenomenon. So suppose we have the problem. So we have the heat release here and study the propagation of wave in this channel. The solution will look like this one. So this is a shock wave with heat release. This state PCG corresponds to this point. And after the compression of the media, you will get the refraction which follows the this jump. And these are the constant parameters. And so it turns out that the parameters here correspond to simple expansion wave, and that's actually also one of the reasons why I built this course in such a manner, because previously in Russia I had a course called reactive flows, numerical simulation of reactive flows. And if you want to explain the solution for this problem, you should first of all explain the shock Rengen-Higuetti jump conditions, and after that you should explain the solution here. And you comes to first of all you should explain the gas dynamics of this problem. What does it mean, a refraction wave, and shock wave, even if we not discuss the numerical methods. Even without logics of Riemann problem solvers for Euler equations, even if you just take a number of problems typical for some area, anyway, the ingredients for the profiles for flow regimes, they consist of shocks, expansion waves, simple waves, and so on. And this solution is also self-similar. So what does it mean? It means that in time, so it will propagate with the same amplitude, and this profile will stretch, and this point where then we have constant parameters. So it's approximately on the middle of this segment, and this on the middle of this interval, and so on. I don't want to to show these formulas how to compute these parameters, but anyway. Another example of the simple waves is the motion of piston. So if you have a tube filled with gas, and you move a piston outside the tube, then the flow that we will have on this tube is the flow corresponding to just a simple expansion wave. This is another example of when you have this type of flow explicitly. Well, okay.